Good afternoon and welcome. My name's Mike Blanch and I'll be chairing the session, and I don't know what I've done wrong, but I managed to also be asked to actually present, so apologies for that. This is our illustrious crew. So we're doing innovation. It's innovation section 5. It's about offshore. So I'll be talking first, then Richard from Quoceant will be talking about wind and wave power combination. David Ainsworth will be talking about the 500 kilowatt. It's not a kit system, it's a kite system. Apologies for that spelling mistake. And then Tim will be talking about multi-rotor devices, a bit tongue-in-cheek, but talking about what wind can learn from Tidal, so I'm looking forward to that. And then Maurizio will be talking about how wind turbine can learn to operate itself from experience. You may have seen that this session was billed as the major EU demo wind and BEIS funded demonstration and innovation projects. And unfortunately, there was an election called, which means that BEIS can't now talk about anything related to its projects, particularly its EU ones. So I apologize on behalf of BEIS. His intention was to announce demo wind projects because I know a lot of the demo wind projects have not been announced. It's very difficult actually to find what's funded by them, but there are some big, significant projects, and they are ones that are worthy of attention, so it's just a great shame that that hasn't come to pass. I wonder if there's anyone in the audience who actually has a demo wind project, because you can talk about it, I can't. Gentleman over there. Yes. Very, very briefly, go on. So what's your name, Ben?
Yeah, name's Ben Yates from Tension Technology International. We're based in Inverness, and we're involved in a Spanish-led consortium, Demo Wind, and it's for a floating semi-submersible type device with heave plates. And what's going to happen is we're installing a 6-scale prototype in the Canary Islands, and under the UK agency, we're being funded to actually develop the mooring system, and our speciality is in synthetic moorings and looking at the kind of cost benefit in terms of loads and footprints for synthetic-based moorings. So we see that as a real enabling technology, and yeah, that's one of the demo wind projects.
Thank you. So that's Ben Yates from TTI. Thank you, Ben.
Thank you.
I'm going to start my presentation now because I'm going to want to talk about the offshore wind innovation landscape. A little bit about BVG Associates. I've been at BVG Associates for 7 and a bit years, and we offer business advisory, economics and technology services, and we're delighted to say we have a lot of the great and the good we've been pleased to work for and with. There's also on our website a whole tons of different reports that are free to download, so please avail yourself of that service. This is a bit about me. I lead our technology strategy, due diligence, and R&D support sector. Basically, we're about trying to help select the best technologies to deliver levelized cost of energy reduction. So I've been there. I've been 26 years in the industry. I think Richard's been 25 years, I think. In 2016, I led an interesting project, and I'll talk a little bit more about it in a minute, which was analysing combinations of different technologies. And I was also seconded into BIS in 2013 to help develop the offshore wind industrial strategy. And of course, we're back at that stage again, talking about what the offshore wind industrial strategy looks like. So, what's the context, the landscape for innovation? Well, I'm going to talk mainly about, well, almost exclusively about offshore wind, but it does have implications. So, there has been an accelerated cost reduction. It's been delivered. So, on this curve of cost of energy in euros against date of first operation, we, in 2015, forecast what is the blue sort of highlighted bit And then we then revised the forecast to this grey highlighted bit, and then various wind farms came in. So we got things like the first UK CFDs came in sort of consistent with that, but then we had a whole host that are lower. This one here is particularly low because it doesn't, it connects into an offshore hub, so it doesn't have the full transmission costs in it. But nonetheless, it's off the bottom of the curve, which is rather super. The black curve is combined cycle gas turbines based on prices that BEIS publish. So this is looking very exciting. Apart from offshore wind being something that was seen as quite expensive, it's now looking very much better. And then even more amazingly, let's go to the next one. This is a recent Dong Gode Wind bid in euros per megawatt hour, and then they bid in nothing, so they're going to get a wholesale electricity price. I'm not quite sure what the implications of that are. It might mean that they get more than 60. They've obviously worked out what the wholesale electricity price is, but this is an enormously successful reduction in cost of energy. Yeah, so some of those sites, so Borselli's site, typically I think you're looking in 70 to 80 euros per megawatt hour as a type of price we're talking about. And then for the UK CFD round, which is just underway at the moment, we're talking about having, well, we suspect winning bids in 2017 prices of £85 per megawatt hour. Now, nuclear Hinkley C is stated to have £92.50 per megawatt hour, but that's in a 2012 price, so it's probably about, you know, over £100 per megawatt hour. So suddenly there's a dynamic is going to shift in the UK, potentially away from nuclear. Very exciting. Offshore wind test and demo opportunities are not so exciting. They have, there is concern because offshore wind's got cheaper, the next CFD round is going to eat up more capacity, and so there's now a concern that there isn't enough supply of consented sites. So that could be something that limits price reduction, certainly in the UK going forward. And new sites, new wind farms need to really have included in them sites for test and demonstration, and I think that will form part of the next industrial strategy. So we're talking about innovation, we're talking about technology, improving that, but we just need to remember that there are various things going on that aren't to do with technology. So here is an example of a cost that you might start off with. The cost, we expect various things like development, turbine innovations, foundations, etc., all to eat away at that cost with time. But let's not forget there's also supply chain elements and finance, and so cost of energy reduction does depend on them too. Yes, and just because we've had rapid cost reduction doesn't mean that it will all continue at the same pace. And also, when you see bid prices, they're not quite the same as LCOE. You need to translate between them. Recent LCOE reductions have been a happy coincidence between bigger turbines, but the innovation that's come from that, cheap steel, but also cheap finance. If finance goes up, of course, other costs are going to increase because your LCOE calculation requires you to include a weighted average cost of capital. So you can't count on chickens. That's why innovation still remains essential if offshore wind is to continue to reduce its levelized cost of energy and can become increasingly competitive. Source of new electricity generation. It's new electricity generation. It's not, we should give up talking about renewables because it's mainstream now. So, I'd like to think, where are we, what are we innovating for? So if we stick with conventional wind, we're probably looking that turbines are going to grow in size, they're going to continue. This is a trend, slightly out of date one, because some of these have been rebranded as higher rated power turbines. But what are we looking at? We're looking at something probably with a 12 megawatt, roughly about 200 meter rotor, hub height of 130 meters. And what's it going to weigh? It's going to weigh in excess of 500 tons. So this is a big beast. So what's the implication then on innovation for vessels? Well, We think collaboration is vital. Too many people have been surprised by 8 megawatt turbines appearing, and a lot of investment in turbine installation vessels was done, but it wasn't necessarily done for the right size. Upgrades to vessels can be a stopgap for that, but it's a bit frustrating. And there aren't really any vessels over 10 meg that can install things over 10 megawatts, so that's a big challenge. And when people committed to investments, probably in 2010 or 2012, the actual market size was much bigger as well. So there's uncertainty about that. So is there a business case for new vessels? That's a question to ask. And manufacturers of turbines, are developing new turbines, but is it something that they can realize the benefit of? If you're still dealing with installation inefficiently, then your ability to realize the benefit of the larger turbine is compromised. Siemens, for example, has made long-term commitments to things like service operation vessels, but not necessarily the vessels to install turbines. So on vessels, I'm saying that there are probably a need for a radical rethink. Do we swap to doing something very different? This float out or float and submerge. It used to be called float out and sink, but sink was seen as being a bit of an unstable process. And one of the exciting projects I think that's going on at the moment is that Blythe Offshore Wind and BAM are building foundations that are, certainly for the foundations themselves, are float and submerge. They don't have the turbines or won't go out with the turbines on them, but you can see that as an important step going forward. For foundations as large as turbine means, in the last talk, someone was saying how monopiles had surprised everybody by being their longevity, their ability to grow in scale. But that's something that we know has happened, but will it continue to do that? And then the other thing is speed of installation. This is very important. Boom lock. Hywind came to us with their boom lock idea, and we talked about CapEx spend and OpEx spend and what have you, and the effect of that on their boom lock innovation. But the important thing actually was that the speed of installation was critical. So you see here what it was before, the spending profile on the left, and just to remind you, finance can be a massive part of the levelized cost of energy. And so what happens if you shorten the build? Well, you get this type of effect. The pie gets a bit smaller, and that's an important form of innovation. Also, what about combinations of different things? We tend to think in our own silos about offshore wind, but Richard's going to talk a bit more about combination later. And here is a project, a Marabou project, where we looked at different combinations. One of which was about mussel farming and offshore wind. Does that work? Does that stack up? Particularly as there is an EU multi-use of space directive, which is trying to encourage people to do that. And I think places like Belgium will see more of that. And there were some other very interesting concepts we looked at as part of that project. This is a floating wind wave device, floating power plants, proposed P80. That is, has an 8 megawatt turbine on it and 2 to 3.6 megawatt wave power combined. Is that something we will see more of? This is Eco Wind Water's floating wind desalination multiple use platform. It actually produces water because in Greece the cost of water for islands is quite prohibitive. So that's another form of innovation. And what other sort of innovations might we see? Well, we know that blades are getting bigger, so just pitching them doesn't quite work as well as it used to. So more aero control, floating, and there's a whole session devoted to floating earlier. Multi-rotors, for example, and kites. David's going to talk about kites in a minute. But all have inherently good features to them, but can they deliver levelized costs of energy reductions that are sufficient? So, in conclusion, innovation is needed. The rest of industry needs to keep up with turbine manufacturers. And we're looking at bigger, larger, heavier turbines. We're looking at fewer foundations, cables, and installations per megawatt. So that business case probably gets a bit weaker. Float and submerge, I think we're going to see much more of. And there's going to be more pressure for multi-use of space. The disruptive technologies, which I include kites and floating, now need to demonstrate greater levelized cost of energy reduction because offshore wind has been so successful at driving that down. Just to say, I've put in my presentation, and I'm not going to dwell on it at the moment, but I've put in a list of what I can tell you about the Offshore Wind Technology Program, which was a program that DEC ran, and I put in a list there of the different projects that were part of that. So they covered things like turbine, operation and maintenance, foundations, and electrical infrastructure. So that's there in the record for your record. But we couldn't really talk about demo wind in terms of what projects are being funded. They cover a number of areas which are listed there. The demo wind budget was significant for demo wind 1, which was 31 million euros, and the second demo wind 2 was 24 million euros. It's to be continued. There are people, and we heard from Ben earlier, who have projects. One of them, which is in the public domain, is the Ore Catapult's testing of the 88-meter blade that Adwin have had produced for their next 8-megawatt wind turbine. So it's good to see that. And there's things of funding to be aware of. Innovate UK has a stand here, so do go and talk to them about things like the energy catalyst and infrastructure systems. There's always the EU SME instrument, which is quite a good funding one, and BEIS has an Energy Entrepreneurs Fund, and the last round of that had no successful wind projects in it, so please have a go. So, thank you. We tend to flag these things up in our newsletter, so if you want our newsletter, let me have your card and I can make sure you're on our mailing list. Thank you. Oh, this was just on the CFD timetable, but I can talk about that some other time. Good. Okay, so my pleasure now is to move on to the next speaker. The next speaker is Richard Yemm. Richard and I were just saying that we've been around for too long. Not quite. But he founded Polamis, and he's been very successful in the renewable energy industry. He got a Contribution Green Award in 2011 and the Saltire Prize Medal in 2012. And he co-founded Quoceant, and I hand you over to him to talk about offshore wind and wave power technology. Thank you, Richard.
Good afternoon. I'm delighted to come and talk on what is actually quite a different topic for me. I've probably given hundreds of presentations on Polamis and on wave power in general, and this is actually an exciting new topic for me, and hopefully I'll be able to project that to you. Just for those of you who don't know the background, in 1998 I founded was Ocean Power Delivery then, became Polamis Wave Power to develop, which is probably still the most accomplished and demonstrated and iterated wave energy technology so far, the Polamis system. Sadly, in November 2014, it became clear that we couldn't continue the funding of that company, and sadly we had to put it into administration, but there was a real determination. It was 750 engineer years of activity, 95 million pounds of investment across 6 full-scale machines connected in 2 countries to the grid, including 2 small wave farms and all of the necessary infrastructure for that. And we were determined that this learning was not going to evaporate back to the ether, that we would keep it in a lifeboat, and that lifeboat became called Quotient. So now we're consultants, so we're selling that expertise and that knowledge into your development programs to help you genuinely cut corners, to shave years and hopefully millions and mistakes out of your programs. But we're also trying to look forward. How can we use this experience? How can we apply it to other areas of renewables? How can we bring that expertise to bear on other sectors? And one of the very obvious adjacent ones for us is deepwater offshore wind. And we're talking the more exposed sites. We think the majority of the global offshore wind is open ocean. It's not like the North Sea, It's deep water, it's rough, and that is our area of expertise operating in that environment. But I guess firstly, I just wanted to make it absolutely clear that we're not proposing this. This is absolutely not what we're proposing. So very different technology for a very different application. So firstly, just to very quickly run through the drivers, and the drivers always have to be this triple bottom line: cost of energy, security of supply, and CO2 reduction. And in researching this talk, with a rising sense of panic as the day was approaching, it really became clear to me that there is actually a very strong case, and hopefully I'll articulate that to you through this talk. So cost of energy primarily through lower cost and higher availability. We'll come back to all of these, so I'll go quickly. Firmer, less intermittent supply. There's good aggregation story here. And obviously, all of the kit that goes in the sea and all of the vessels that are operating it takes energy, so we're looking for the maximum return in terms of generation on that embodied energy. So in summary, offshore wind, I think the thing that makes this worth looking at again is offshore wind is moving to deeper, rougher sites where incident wave energy is actually meaningful. For a long time, wind has been in a very, well, relatively sheltered environment. The scaling up that we've seen that Mike talked about, staggering levels of scale up. I mean, this is now foundations where the wave loading is becoming a significant proportion and perhaps even dominant in the loading of the foundation. I think the really exciting part, and the case that we're looking at it again very hard, is this very actually weak correlation short term between the local wind speed and what the waves are doing. And when you actually zoom down into what drives the structural cost of a foundation, the extreme loads, there's zero correlation between peak wind speeds and gusts and large waves. So the high fixed and capital operating costs of offshore wind and wave systems traditionally been a barrier, but if we can share those costs, then it's potentially exciting. And the timing is good, and I think this is really why I'm keen to be giving this talk now, and that's identified it as a priority, is deep water wind is not certified up to the eyeballs yet. There's an opportunity to interact and change and modify the technology at this stage, which is not there for fixed conventional offshore wind. So firstly, very quickly on the combined resource, there's actually quite a lot of information available on the web. There's some very good peer-reviewed papers. First thing we notice is that, and I think absolutely essential, and it would just be a non-starter without it, there's actually a very strong annual average correlation between a good wave resource and a good deep water offshore wind site. So where it's windy, it's wavy, and it's an exposed ocean, you're going to get both wind and waves. So on an annual average basis, there's a case to deploy both technologies on a similar site. But on a shorter term basis, so we're talking everything from hours, week, days, month, diurnal even, daily variations, the two resources are actually quite weakly correlated. There is of course a correlation, but it's phase shifted, and certainly the peaks don't occur at the same times in almost all cases. So there is a significant aggregation benefit possible, and those benefits vary site to site. You won't be able to read the plot in the middle, have a look when it's online, but actually this is California. So bizarrely, it's windy in the summer and it's wavy in the winter. So actually there are some for particular sites around the world, the aggregation benefits may indeed be extremely significant. So the barriers so far, and I think we've all been part of it, and me included, each industry has pursued its own trajectory. And now, I guess the thing that's making us having to rethink it is now conventional offshore wind has reduced its costs so much, we're all having to come up with much more compelling arguments for why our technologies are still relevant. And I think Mike made a very good point. Floating offshore wind, deep water offshore wind has got a case to make in terms of its cost of energy trajectory as well, so that's helpful to us. So the big question, and the sort of central question, is sort of co-locate. This wasn't meant to be poetry, but co-locate or integrate. So that is the big question. And at Polaris, we actually did a lot of work on co-location, and there is actually quite a compelling argument for co-locating in the same vicinity, sharing grid connections, perhaps sharing electrical infrastructure and tieback and so on. Better utilization of that makes sense. And there are a number of exceptions to that. I think floating power plant, perhaps the most prominent at the moment. So while there were clear benefits from co-location, to have maximum impact, and this is as a result of some points I'll come on to in a moment, I think actually there's a much, much stronger case now for integration rather than just putting a wave farm in the same locale as an offshore wind farm. A number of reasons behind that, which we'll come back to, so I'll just skim through just now. The kind of foundations required, these are enormous foundations. They're like what we would have called in the industry skyhooks. They're sort of like a fixed reference frame for a wave energy converter that a smaller turbine would never have been able to provide. The integration between these factors means that we can be looking at sharing something like a third of the cost, the capital installed cost of the system, at very little marginal additional cost, and I'll come back to that in a minute as well. Storage, both technologies actually require storage. The infrastructure of an offshore wind farm is actually rated for short-term instantaneous peaks. It might be 10, 20% higher than the average long-term capacity. There is storage in the rotor dynamics, but only a finite amount. Wave energy needs storage across waves, and we should note there is zero correlation, none, between wave groups and the energy in an incident wave stream and gusts and fluctuation in the wind stream. So very strong argument for smoothing benefits, and so on. Perhaps at the center of it is sharing loads, and I think the sort of examining this, the nature and the weakness of this correlation, particularly on short-term basis between loads and wind loads and wave loads, is fascinating. And indeed, if you look at what dominates the design of both structures, it's fatigue, and that will be there, whatever, but it is also extreme loads, and it's the lack of correlation between extreme wind loads and extreme wave loads that is particularly interesting. Just before I go on, the weak correlation in phasing is really important. If you look at the time series of wave energy versus the time series of wind, they are very rarely well correlated. There's always a phase shift. The waves arrive first and go sooner, or the period shifts and the energy drops, or the waves persist for longer afterwards. Actually very weakly correlated in terms of peaks hitting. You need to cater for that, but we can do that in an operational sense, not in a design case. But it doesn't stop there. There's obviously a whole raft of benefits, huge topic in terms of potential benefits, in terms of OpEx and availability. And sharing common systems means you can get some benefit, but actually integrating them onto a given platform gives you the most potential. There's lots of work being done, various European funded projects looking at the wave height reduction impact of a wave energy system co-located with an offshore wind farm. And normally people sort of poo-poo this idea because of course people are thinking breakwater for big waves to prevent damage. But if you're looking at access to turbines, actually the reduction in significant wave height and the lee and the sheltering can actually be very significant in the context of access to large offshore turbines, so not to be sniffed at either. Overall, we anticipate there's actually for these larger turbines in these rougher locations, those two caveats, there are some pretty spectacular benefits on cost of energy reduction for available. And it may be, and this is a really kind of key point, it may be that this is a key option for deep water offshore wind, which is now very much off the coattails of conventional offshore wind. It's about reducing the cost of energy, and this is a way to pitch it, of that commercializing floating turbine as it goes through its journey and tries to catch up and indeed become competitive with conventional offshore wind and solar. So the next point is the timing, the alignment of the stars and planets or whatever, the sort of time is nigh. And I think there's a critical point here, because we spent quite a lot of time talking to offshore wind, looking at how we could integrate, talking to oil and gas, how we could integrate our system with them. And the problem is these industries are now certified up to the eyeballs. Nobody will let you put any piece of equipment anywhere near them because of the certified designs, all of the accepted risk profiles that people invest on. But that is not the case in a floating or a deep water fixed foundation. These are not certified as yet. The know-how and understanding of our old industry, the wave energy industry, has never been better. We understand the kind of machines that we could apply to this, and indeed we can envisage some much more effective machines if we had a foundation like we would have on offer in this system. And I think critically, the opportunity for pilots with a sort of realistic commercial perspective and consequence are available. There's a number of floating demos going in around Europe, and they will scale up, and there is an opportunity to get in the water on someone else's capex, if you like. Put the two together to get a better project. And while I think there are some credible offerings out there, I think there are some potentially significantly better operating principles and technologies out there that could be brought to apply. But it's a closing window, and we need to move fast if it's going to be there. Perhaps 5 years to establish, and then the industry will be becoming conventional, will be becoming certified, and will be close to this opportunity again. So just in conclusion, what we bring to the party, I think we've got a great set of experience. We've got fine credentials in the wave energy side of this, in moorings, in connection, in O&M strategies. But Polaris isn't the answer. It was a joke, the first slide, but it is serious. This is a very different type of wave energy challenge to the one that we have faced before. We think there's some very targeted further work that could be done to illustrate and articulate this point and make a very compelling case to the floating wind guys, who will be skeptical on cost of energy, and build ourselves into some projects. And we're currently assessing the appetite for this work. Does anybody want this? And we'll do it if nobody wants it. So we're very keen to speak to people who are interested, who'd like to get involved. Obviously, you'd like to potentially fund this type of work as well, both cross-government and industry. So please get in touch with us or contact us on the website. Thank you very much. Sorry, about a minute over, I think, but hopefully got through it all. Thank you.
Thank you, Richard. What I'm planning to do is we've got a panel session at the end, and if you can hold questions for that, that would be super. My pleasure now is to introduce you to David Ainsworth, who's the interim CEO of Kite Power Systems. He's a chartered engineer with a degree in aeronautics and astronautics, from University of Southampton. David was at KPS in 2014. Prior to that, he worked for 11 years for a Tidal technology developer. And you've been combining your aerospace and renewable technology experience together, which is great to see. And you recently received significant equity, KPS from Shell, E.ON, and Schlumberger to fund development of 500 kilowatt Kite, which you're going to talk to us about. Thank you.
Okay, thank you for the introduction, and good afternoon, everybody. So this isn't the comedy session for the day, this is serious. So Kite Power Systems, who are we and where we've come from. So I wanted to tell you where we've come from, where we are now, and where we hope to be in the next 10 years. So this is just a quick snapshot of today's position. So our brief history, we were founded in Essex in 2011. We merged from two technology streams. There was a very clever individual who basically had a patent for a unique technology to develop kite energy systems. He went to see our founder directors and said, could you build me a demonstrator of this? They said, it's a really nice idea. Won't quite work in that format. We'll do some work on it. And that's when Kite Power Solutions, as we were called in those days, was founded. From then, we sought some funding from Shell's from the Energy Entrepreneurs Fund from DEC in those days, and Shell's Pathfinder and Game Changer programs. And that basically funded the first 4 years of the business. And in that period, we were very much below the radar. We were just basically running out of a small engineering facility in Burnham-on-Crouch in Essex, and testing on a field in near Bradwell-on-Sea nuclear power station. In 2016, we received a significant grant from Innovate UK, and that grant actually included, it was quite a large consortium. It includes Imperial College, it includes BVG Associates, it includes KML Maritime, National Composite Centre in Bristol, and Bank Sales in Southampton. And that program was basically to take the 40 kilowatt system and scale it up to a 500. Also in 2016, we spent a lot of time actually finding a permanent home for this technology. The Bradwell-on-Sea site was great for taking out a bus, erecting the system, testing it on a daily basis and taking it home. But moving forward, we needed somewhere where we could actually permanently deploy it and permanently test it. So we're very pleased to say that we identified a site in late 2015, went through the consenting process in early 2016, working with Natural Power Resources down in Dumfries and Galloway. And we actually received planning consent in summer of 2016 to deploy the system permanently. And also in December 2016, as Mike says, we actually closed our first equity round. So, where are we now? In January, we physically up sticks from Essex, and we totally moved the business to Glasgow. And that decision was based on, we needed to grow the business very, very quickly. We were 8 engineers down in Essex. We needed to double, even treble the size of the business very, very quickly. And we needed a strong pool of resource and know-how to actually draw on to actually expand the business. So we came to Glasgow, which is about an hour and a half's drive from the test site down near Stranraer. So we've actually tripled the staff from 8 to 25 people in the last 5 months, and we're about to take on another 4 in the next 4 weeks or so. So we are expanding at quite a significant rate. We are building the 500 kilowatt system. There's some pictures later in the program, presentation, which actually show you where we are at the moment. We will be deploying this summer, and we will be doing the first flight testing, hopefully in autumn this year. But how does the system work, and how do we generate electricity from kites? So this Mickey Mouse diagram in the top right here is something which is very historical. This goes back to some of the first concept sketches going back to 2011, so we'll still like to show us where the history's come from. But we have a kite, which is a crosswind kite, so it's very, very similar to the kites which people use for kite surfing. In fact, our kite is designed by one of the world's best kite surfing kite designers. He is actually now an employee of KPS, and he works for us full-time designing and developing our kites. So a crosswind kite, basically, it will fly downwind. Sorry, it flies across wind, and as it's flying across wind, it's actually generating lift. So it's not just the wind blowing into the area of the kite is actually generating lift. And that kite is flying away from the base station. As it pulls away from the base station, it's generating around, as Ben will know, about 30 tons per megawatt tension in the tether. So that tether basically pulls the additional tether from the drum rotates and generates electricity. In our case, we're actually generating hydraulic power. We store the hydraulic power in accumulators, and we can then feed that power into a motor generator system to actually provide smooth, consistent power into the grid. Typically, the power generation stroke is taking around 40 seconds, and then the recovery stroke takes about 20 seconds. And the recovery stroke consumes around 5% of the overall energy we generate in a cycle. So to plug the 20-second gap, we have 2 kites flying at the same time. And the neat trick there is something that we discovered when we were working with Mike, is we actually overlap that energy. While each kite may be rated at 500 kilowatts, the overall system rating is probably 10% higher. Okay, so that gives you an idea of where we work. As Mike said, I mean, we're very lucky to have such a strong investor set, and these investors are there basically to pull this technology through. They see significant market opportunities for this in the next 10 to 15 years. This is Schlumberger's first investment in renewables, which is really, really unique for them, which we're really pleased with. Then we have Shell, who's basically been with us since 2011, and E.ON, who are new to the... Basically, they have been watching Kite energy system development for the last 4 or 5 years. They looked across the sector in the back end of 2015, beginning of 2016, and decided it was time for them to make an investment. And they invested in KPS in December 2016. And one of the things that E.ON is doing in parallel to that investment is they actually are looking at demonstration sites as well. So they are looking at funding a demonstration site in the Republic of Ireland for airborne wind energy systems. We're not alone in this space. There's probably about another 10 developers in Europe developing similar systems. And as I said, we've actually had an investment from BEIS or DEC as they were in those days, under the Energy Entrepreneurs Fund. We've got the Innovate UK grant. So this is a picture of the test system in its mobile configuration down at Bradwell-on-Sea Nuclear Power Station in Essex. So the benefits. Why do we see this technology as significantly different from horizontal axis wind turbines, and why do we see that this is actually a significant disruptive technology? And it all comes down to the levelized cost of energy and the potential IRR that the investors can make on this technology moving forward. And what we've done is basically, we've looked at significant onshore modeling, significant offshore modeling. We've done a lot of work with BVG on this, I think probably over 3 years now. It's been a long time. And we're consistently updating this as the design evolves. And the biggest impact that we have at the beginning of the stage is basically our mass is the biggest driver on cost. The mass drives the capital cost, the mass drives the installation cost, the mass drives the O&M. And our mass for a on or offshore system is typically around 15 to 20% of the mass of an equivalent rated horizontal axis wind turbine. Then we look at the capex, because the mass drives into capex. Maybe onshore we don't have so much of a benefit, but when we look at 40-meter plus depth offshore, our capex is significantly lower than offshore wind. Our yield is slightly higher because we're flying around twice the tip height of a similar rated horizontal axis wind turbine. And what's important is to notice is that while you may hear people talk about high altitude wind, we're not high altitude wind. We're still 500 meters, 450 meters. This is still sort of fairly low altitude. So we mustn't get confused by that. But in that gap between the tip height of a wind turbine up to the 500 meter mark, there is more, we're slightly higher in the shear zone, so there is more energy to be had. Our O&M costs in the early days, we're really penalizing ourselves. We're saying this is an infant technology. Our availability isn't going to be as good as a mature technology, which has actually had 40 years R&D behind it and 40 years in-field demonstration and development. So we're penalizing ourselves in the early phases of an early demonstration project, so we're predicting our O&M will be higher. But even then, if you look at the relative the IRR improvement over onshore and offshore wind, typically offshore we're going to be around 40% higher IRR, and onshore we may be something like around 25% with reasonably mature technologies, but first of a kind, we could even be sort of 5 to 10% higher than mature technologies. Levelized cost of energy, yes, we're going to be probably around 2/3 offshore and probably around 75 to 80% onshore. But these are, like I say, these are constantly evolving numbers. As we improve the modeling, these will actually get better. So this is just a bit of a shout out to who we're working with at the moment on the supply chain side of things. And the picture on the left is the image of what will be installed at West Frew this summer. And the photographs on the right are pictures of the system as we're progressing. So I think this isn't it? So this thing here then, this is the first 500 kilowatt kite. This kite is 70 meters squared, so it's around about the size of this stage. It's about 17 meters tip to tip and about 5 meters span. So those are being produced for us at the moment. The first one's been delivered, as you can see, and they will be constantly evolved and adapted over the next couple of years. This bit here is the turntable. There is another picture from earlier this week, which is now painted and actually mounted on the trailer. So unfortunately, the deadline for this was before I actually had that picture. And then these bits here are the winches, which sit just above the pulley. So this bit here is this black and yellow hash bit here. So this work is basically, it's all been, the significant fabrications have been done for us by Goodman's in Nottingham, and all the assembly, testing and commissioning will be done at Kelwoods down in Dumfries, about 80 miles south of Glasgow. So we have RCG supporting us very, very heavily with the CDM process on this. This is a novel technology. It's the first time a CDM process has been undertaken on this technology. So this is quite rigorous. And also the test site that we're using is actually making it even more rigorous. Natural Power have actually helped us through the consenting process and are helping us with our environmental monitoring moving forward. So the future. So where does this technology go? So we are planning basically to actually have our first onshore arrays, pilot arrays, somewhere in the UK, somewhere around 2020. And we're looking at pilot demonstration projects now, where we will be putting in maybe 10 500 kilowatt systems to build a significant number of fleet hours. The floating structure on the left basically just shows a simple spar buoy, and this basically is a technology which can be used in anything from 40 meter plus water depths. So that actually gives us a significant benefit over some of the horizontal axis wind turbine floating configuration options that we're seeing, which are limited to 100 meters plus water depth, but there are some solutions out there for the 40 to 100 meter water depth. The benefit about our technology is we don't need anything significant installation vessels to install it. One of the other big market opportunities that we see coming in the 2020s is repowering the existing horizontal axis offshore wind fleet that's out there. Between 2022 and about 2028, there'll be about just around a megawatt of 2.3 to 3.5 megawatt turbines coming into the decommissioning end-of-life phase. If we take the towers off, we take the nacelles off, we take the blades off, and we just basically bolt an adapter piece onto the top of the existing transition piece, we could repower those and get another 10 or 15 years life out of them. Because the loads that we put onto those structures are so much lower than horizontal axis wind turbines. And one of the overriding benefits of our technology is the portability of this. We can pack this up into 2 or 3 ISO containers and transport this anywhere in the world. We're not looking at basically trying to transport 80 to 120 meter length blades by road or ship. So it opens up a whole new opportunity to us in isolated markets. So, sorry, I've run over a bit, but that's me. I'm David Ainsworth, Business Development Director. We're based in Glasgow, and like Mike says, happy to take any questions at the end of the panel sessions. Thank you very much indeed.
Thank you, David. It's my pleasure now to introduce Tim Baker, who's a Technical Director at Veatch for Tidal Energy. He's been in professional experience he's had for 17 years, most recently as a technical lead for the design of a 3 megawatt multi-rotor support structure, the ETI's 7.5 million tidal energy converter tech system demonstrator. Tim has also been the lead engineer for a tidal turbine developer, where he had responsibility for the technology development, design and test program. So Tim heads up Veatch's offshore wind design activities in Europe, drawing on similarities between the industries. So he's now going to talk to us about the multi-rotor device, which can offer what can offshore wind learn from the tidal industry? Thank you, Tim.
Thank you for the introduction. Obviously, just to explain my tongue-in-cheek title, it's obviously very much accepted that nearly all of the learning has transferred from wind to tidal, not the other way around, but multi-rotor structures is an interesting area where there are potentially some useful bits of knowledge transfer back the other way, and that's my hope to talk to you today. So why am I standing here? Well, Veatch is around 10,000 people worldwide, a global construction consultancy company. We're involved in all forms of renewables, in particular over around 10 gigawatts of wind projects over the last 15 years. And most relevant to today, as the introduction said, we've just finished detailed design of a twin rotor 3 megawatt tidal turbine structure. So I'm keen just to share with you a few examples of multi-rotor turbines, both in wind and tidal. I'm going to talk about some of the cost drivers, again comparing the differences between wind and tidal, and then finally a bit of hopefully knowledge transfer from one industry to another. So a few examples. So in tidal, we've had operational devices in the water for nearly 10 years, going back to 2008 with the twin rotor marine current turbines device, which is in Northern Ireland in Cranfield Loch. That's operated very successfully for a number of years, and there's a huge amount of operational data that's been gathered from that device. There have been a number of other structures, so examples, Scott Renewables, 250 kilowatt demonstrator at EMEC, and last year, 2016, their commercial scale 2 megawatt device. There are also a number of tidal structures in the design phase, so I mentioned the Veatch ETI Atlantis twin rotor structure. Tucado, to bring some examples, have got a 4-rotor structure in the design phase, and these numbers of rotors go right up to something like the tidal stream shuttle hydro device to be installed in the Force site at Canada, where they've got 36 rotors. So we've got a wide range of experience of different numbers of rotors and multi-rotor structures within tidal. In wind, there's been some experience, and going back to 1995, there was an initial 6-rotor structure, which was then reduced to 4 due to dynamic concerns. And recently, in 2016, a very successful test from Vestas, their 4-rotor device, and that's obviously been very positive. As we're all aware, there are a number of multi-rotor offshore wind structures in the design phase, and I think that's why it's really timely maybe to try and share some of this learning from tidal. So, very quick look at the cost drivers. So, I'm going to share some of the results from a tidal project that was done. The graph you can see bottom right, the letters there on the bottom represent a different configuration. So, this could be multi-rotor or single rotor. It could be different electrical configurations, different support structures. I'll not focus on the details, but the conclusions are interesting. So we did a complete holistic approach to levelized cost of energy, and you see from there that the multi-rotors came out the best, but for a comparable configuration, the single rotors were not far behind. I think what's interesting there, we did a very robust error analysis on that, and you see from the error bars that there is considerable overlap. So the main conclusion I draw from that is, yes, multi-rotors came out best, but it's not in all cases. It's very much site-specific and project-specific. I'm going to just do a quick comparison of some of the tidal drivers. So we've got a schematic on the left here just indicating, let's compare two monopile structures against two rotors on a single structure and have a look at why we might do that. So interestingly, at first value, you just look at this and say, well, we wouldn't do it. The fatigue is much, much more difficult. The mass is higher of the structure itself. The cost of the structure itself is higher. All worse for the multi-rotor. Why would you do this? And it's very much that it's a whole system balance that means it's a good idea. So the things that help us are we have reduced installation costs, we have reduced cabling costs, both installation and capex, and we see some significant performance advantages in terms of reduced wakes and also increased capacity factor, increased yield due to blockage from the proximity of these rotors. If we compare that to the drivers in wind, it's very different. So looking back over the last 30 years or so, back to the 1980s, as we saw earlier, we've seen year-on-year increases in rotor diameter for very good reasons. We're getting into higher speeds, higher altitudes, fewer turbines, reduced installation cost. But we certainly got to ask the question, does that trend just continue forever and ever? In particular, the scaling of blade masses and costs, both their capex and also their transportation and handling, is very, very non-linear as you start to get to these very large rotor diameters. So there's certainly a question of, is there a place for a multi-rotor structure in wind? Going to move to the final section, which is a bit of knowledge transfer, hopefully, from Tidal. So the first thing I wanted to talk about was wake effects. Obviously, a key driver in terms of size of site, the spacings, and in the early days of wind, there were a lot of lessons learnt there in terms of how they interacted and what that did to the bottom line IRR. So here's some data from Tidal. We're comparing at the top a single rotor against an equivalent three-rotor system in the bottom screen. We're just showing the velocities in the flow with the colors, and I think just immediately you see that the wake recovery is much, much quicker in the multi-rotor. So that obviously gives you advantages in terms of spacings and also in terms of performance. We see a similar picture there in terms of the level of turbulence that you see, which is much lower behind the multi-rotor. There's also some really useful test data that we've got in the tidal industry. So I'd refer people to the ETI's Perawatt project, which did a lot of wake and blockage test modeling. So we've got here a configuration of 3 rotors and 4 rotors in close proximity. And you can see we've got very close correlations in between the crosses and the solid lines there between modeled and test data. So there's lots of really useful learning there, which is applicable to wind as well. I'll move on to talk a bit about confinement of flows, or blockages it's sometimes called. So in simple terms, looking at the pictures on the left, if you put a turbine in a tube, or if you put it near to other turbines, you get some confinement of the flow. That causes more energy to go through the turbine, and you see higher powers, and you see higher capacity factors. I think the interesting conclusions we've seen in Tidal are that we see that although the fatigue loads go up, the ultimate loads are generally unaffected by this, and we're seeing a benefit to capacity factors. A few examples. So in Tidal, the top graph shows broadly 10 to 12% increases from proximity of 2 rotors. One question we asked is, well, how close can these rotors be together? As you go along the graph from right to left, we're moving those rotors closer together, and we're seeing small additional increases in the power output. In Tidal, we find we can actually bring them as close together as we would want to. That's partly because of the viscosity of the fluid, so the wakes don't spread out. I suspect in wind, where you've got a different viscosity, you'll find similar things but a different balance, and there may well be limits there. I'll just show you, for comparison purposes, a wind example as well. This is from Peter Jameson's work, and he shows both a 7-rotor and a 45-rotor wind example, giving the order of 3 to 10% improvements from blockage effects. So these are generally useful things to be harnessing. The last section, I'm going to talk just quickly about a few design aspects that have been learned. So we've done quite a lot of work developing the standards. If you imagine that you've got more than one rotor, there's a number of different combinations. You could have one rotor in normal operation. You could have a fault case on another rotor generating higher loads. It's really important to understand the likelihood of those occurring, and if you don't do that analysis really rigorously, then you end up very much over-designing your turbine. It's complicated with just 2 rotors. As you go up from 2 to 3 to 4, the numbers of load cases, design cases to consider exponentially rises. So we've done some work, and we've worked with DNV GL on this in terms of developing those standards and approach. So again, that's something keen to share with the wind industry, that we've done some robust analysis on that, which again is directly transferable. The final slide I've got here is just a quick walk around the turbine in terms of some of the challenges and opportunities that we've seen. So in terms of challenges in multi-rotor structures, I think the dynamics has certainly been one of the major issues. As part of the work we've done in the industry, we've developed some methods for both prediction of these dynamics and also management of difficulties. We've also found that in order to get the best cost of energy and the best mass cost optimized designs, we've needed to go to some quite complex finite element design approaches. And so in order to couple that with some of these complex loadings, we've had to develop some new techniques there as well. In terms of opportunities, there's a few that are specific to the size and shape of a multi-rotor. So we've seen that by streamlining things, we've been able to increase energy yields. It prevents the flow being diverted away from the turbines. And we've also found ways to reduce some of the fatigue loadings, again, by the geometry that we've used. Typically, horizontal members are giving us better blade pass fatigue than you'd see from vertical members, such as a monopile. And the final point is that we found some cases where if you've got multi-rotors, then contra-rotation, some clockwise, some anti-clockwise, has given us some benefits. Some cancelling of torque loadings there, and that's been very useful in optimizing the design. So that's just a quick flavor, really, of some of the things that we've learned. I'll just sum up, really, I guess. So in terms of conclusions, multi-rotors, definitely significant potential for helping levelise cost of energy. Very much transferable and applicable to wind as well. Are they always the correct solution? No, absolutely not. It's very much site and project specific. Many challenges still to overcome. We talked about the risk profile earlier, about what's acceptable. Huge risks and huge unknowns, and an R&D that's required. The tidal industry has learnt some of these solutions, and we're very pleased to share that. Thank you very much for listening.
Thanks, Tim. Since you've kept to time, do you want to answer a couple of questions? Would that be good? Yeah. Any questions for Tim? Okay, can't see any. Right, well, we'll move on then in that case. Thank you, Tim. It's my pleasure now to introduce Maurizio Collu, who's Senior Lecturer of Dynamics and Offshore Structures at Cranfield University. He leads the research on floating foundations for emerging renewable energy industry. He led the design of the support structure in the 2.8 million ETI-funded project NOVA, and the development of a coupled model of dynamics for floating wind turbines for the €6 million project H2 Ocean. He's on the ITTC Ocean Engineering Committee and on the RINA Marine Innovation Committee. So I'd like to introduce Maurizio. Maurizio, all yours. Thank you.
Thank you very much, Mike. Today I'm going to speak about, let's say, a very innovative idea and something that we are just starting to think about at Cranfield University. And the question is a bit strange. Can a wind turbine learn to operate itself from experience? So the focus is, rather than us designing the control strategy of the wind turbine? Can the wind turbine learn to operate itself according to an objective? It's a strange question. But this is even a more silly question. Are you able to work? Now, you came here by working, right? And then you know these equations. These are the equations from a paper talking about bipedal working. Clearly not. So how is possible that you don't know the equations under your dynamics of working, but you're perfectly able to work? Well, maybe something similar to this happened some years ago. You basically did a trial and error, and your brain processed your experience in order to work a bit better every time. By the way, this is my daughter learning to work a few years ago. Successful up to this point. Anyway, so there is a mechanism that allows systems to learn to operate itself. Well, it's a bit crude to define my daughter a system, but basically, without knowing in details the equations behind the dynamics of the system. So, can we do the same with wind turbines? But the very first question is, why we need to do the same for wind turbines? They've operated themselves quite well so far with the so-called deterministic control system based on a mathematical model. But at the moment, as it has been seen so far in the presentations, we are going toward larger and larger wind turbines. These wind turbines are experiencing more complex loads in general. Not only that, we are passing from wind farms with tens of wind turbines up to thousands of wind turbines. So this means a more complex interaction. Another important point is that many of these wind turbines are equipped with condition monitoring systems. I'm now in a project, a different project, where we basically are seeing that from 80 to 85% of these data are collected and never used, because obviously it's an overwhelming amount of data, and they are used only to trigger alarms, but not to learn from these how to operate better the wind farms. So there seems to be some room to adopt an alternative way to control the wind turbines, more advanced, but every time you talk about advanced control system to wind turbine manufacturers, they're a bit scared because they say every time you have a more advanced system, that's less reliable and more costly. And that is not good. So how can you manage to have a more advanced system, but without complicating too much the control system? How can you have something that is able to better operate with your wind turbine, but without changing the wind turbine control system as it is at the moment? So, as I said, this was a gamble at the start, but we have done some studies and seems promising. What we have done is we have taken a normal offshore wind turbine, obviously not a real one because we cannot play with the real thing before proving our idea. We kept exactly the same so-called manipulated variables. So we gave a brain to this wind turbine, but we said you are allowed to control the same systems that a normal wind turbine control. And in particular, very simply put, a wind turbine, what the two main degrees of freedom are the speed at which it rotates and the angle, the pitch angle of the blades. So this angle can change as well as these speeds. When you have a normal wind turbine operating, basically increasing the wind speed, it starts to rotate more quickly. Then when it reaches its rated power, it starts to pitch the blades because it cannot absorb all that wind energy. So it sheds some energy by pitching the blades. So we said, we didn't say these things to the algorithm, to the brain. We only said, we are not going to tell you how to operate yourself. I'm just telling you that you can control the speed at which the wind turbine rotates and the pitch angle. You have to learn how to operate it. So in general, the very basic objective of a wind turbine, you may think is extracting the maximum amount of energy, but it's not that. The ultimate aim is to produce the cheapest energy possible, because that's what it counts, how many pences per kilowatt hour you pay on your bill. So what we did is we said to the algorithm, okay, LCOE maybe is a bit too complicated as a first step. Start with something simpler. We are asking you, without telling you how to do it, to extract the maximum amount of energy within these wind speeds. Remember, we didn't tell the algorithm how it's done, how is the state of the art. So how can we have the wind turbine having an experience, a virtual experience? So we have a numerical model of offshore wind turbine. There is a very well-known reference system that is the NREL 5 megawatt offshore wind turbine system. We can numerically generate complex wind speeds, so the wind speed with a certain turbulence over a certain amount of time. And we can put together the load cases and the system numerically in a software. For example, we used FAST version 8. But basically, the important message here is that we can have the brain experiencing a real situation with a real wind turbine. So the brain is playing with the pitch angle and the rotational speed, augmenting, diminishing, and feeling what is better for the wind turbine. Now, this graph is a bit complicated, but I walk you through little by little. So basically, the color is the efficiency of your wind turbine. The closer to the yellow, the better it is. So you can see that you can extract to have a coefficient of power around 38.6% around the blue region, up to 43% in the yellow region. So the more yellow it is, the better it is. So high efficiency, low efficiency. On the horizontal axis, you have the tip speed ratio. The tip speed ratio is basically the ratio between the wind speed and the speed at which the turbine rotates. In the initial regime, what the real wind turbines does is to keep this tip speed ratio fixed. So if the wind speed augments, this rotational speed augments. So the ratio between the two remains constant. And you don't change the pitch angle, because you keep it at the best possible configuration. So what you see in red, this is the initial acceleration of the turbine, but basically real wind turbines keep the tip speed ratio fixed and the blade pitch fixed at the maximum efficiency possible. We didn't tell this to the algorithm. So we had the algorithm learning by itself what to do, and we ended up with the blue curve. So it's slightly different than the other one, but as you can see, apart from the initial transient that is the same as this one, the learning algorithm learned to keep more or less the tip speed ratio around this region, around 7, and the blade pitch around this value. So again, the learning algorithm learned by itself what the wind industry, what took the industry several decades to learn, to keep the tip speed ratio fixed and the blade pitch fixed. This algorithm learned it virtually in 1 week of simulations. Obviously, I'm not telling you this algorithm is better than the conventional one, because actually the gain in efficiency that you have, because as you can see, the learning algorithm doesn't know that this is the best way because of load on the blades. In fact, it tends to track the best points on this surface. So it does a little bit better than the conventional one from an energy point of view. So, but the important point, what we wanted to demonstrate is that even if the algorithm didn't know about dynamics, and we didn't tell the algorithm to keep the tip speed ratio fixed and the blade pitch fixed. It learned it by itself. So I'm not so much interested in the energy extracted. I'm interested in the potential that this algorithm has to learn how to optimally control a wind turbine. So what is the takeaway message here? As I said, we are going to have larger wind turbines and larger wind farms, and these are becoming more and more challenging to control. More challenging to control means potentially more complex control systems, but more complex control systems are also less reliable. So why don't try to adopt an alternative strategy? So keeping the same variables to be controlled, so still only the pitch and the rotational speed, using the same sensors, but taking advantage of all the condition monitoring data, and learn how to optimum control the wind turbine. Obviously, since the algorithm seems to work, you can now ask the algorithm not to extract the maximum amount of energy, but to extract an energy at the lowest cost. So he will figure out, obviously optimistically, we are still working on this, how to do that, controlling exactly the same control, using the same control system of normal wind turbines, so it can be potentially retrofitted. One way to explain it better is, at the moment, the wind turbines are not taking advantage of all the condition monitoring data that you have. So it's a bit like you try to learn how to walk using only one eye and not listening to what the other eye, your feet, and your ears are telling you. So there is a huge potential to improve the performance of our wind turbines if we take advantage of all this additional data. So, as I said, our aim was not to substitute the control system to have a better energy extraction. Our ultimate aim is to have a better levelized cost of energy. So the next steps is to ask the wind turbine to learn how to control itself for this aim. Thank you very much.
Thank you, Maurizio. Do you want us to... Are there any particular questions from Maurizio? I certainly have one. What do you think the future potential of this is? I'm thinking that a lot of the times we want to know what fatigue lives come out of the turbine. Sometimes you actually want to run it harder because you know there's a lot of fatigue type left in it. Yeah, so where do you think the future
That's
lies?
actually a very good question, and it's exactly the next steps for our research. So now that in a way we have proven the potential that is able to learn to operate in an optimum way as much as the state of the art is, okay, the objective is not to extract the maximum amount of energy, but extract the maximum amount of energy with the constraint of the fatigue loads on the wind turbine. So if you feel that you're extracting the maximum amount of energy, but this is a too high cost from a fatigue point of view, slow down your wind turbine. So what we are going to do is to use a new objective function, where in that objective function we will also take into account the fatigue loads. And while thinking about this concept, if you take one step forward, is you can take into account aging. It's a bit like a human being. A human being is not as performant when he's young and when he's old. So you can have a old wind turbine still able to perform and not maybe at the same level of the young ones. So what you do is basically to strike the best trade-off between the maximum amount of energy produced, but for how long it will use it. So you may have a 30 years life rather than 25 years if you operate a bit more cautiously during these 30 years. So in a way, you keep an eye on the fatigue loads. If you have a crack, the system, taking advantage of the condition monitoring system, the control system will be able to learn how to adapt to that. So in a way, the potential is what is the most interesting part of this.
Thank you. And I have a supplementary to that because we all know that sensors are somewhat unreliable. What happens, yeah, I mean, I know onshore, we suffer from a lot of turbines. They just trigger a fault when they don't have one. They shut down. You wait for the temperature gauge to sort itself out and start it again. I mean, I know things can be better engineered, but we live with that with onshore turbines. Not so much offshore, because the design has been tried to be sharper and better components, better quality components from the outset. What do you do when the sensors are that you're trying to learn from malfunction?
Yes, that's exactly one other. We have involved in another project called Offshore, has been launched in April. And that's all focused about operation and maintenance of offshore wind farms and how to make it a bit better to lower the costs and the risks. So basically, this, if you want, machine learning approach to wind turbines is used in this way. You basically have 3 groups of people. One is the condition monitoring people. So these people send huge amount of data to a machine learning algorithm, something that can learn what are the patterns between the signals and the problems that you may have. Then this machine learning algorithm says, okay, I've seen this pattern happening before. There is another group that is in charge of the robotics inspection and maintenance. So rather than sending people, we lower the risk and the cost by sending drones, both UAV, ROV, and robots in the substations. And the other group, that is where I am, is trying to make sense of those patterns to have a cleverer monitoring system. So, as you said, offshore is not so easy to send a guy in a van. You cannot. And there are strict limitations in terms of sea state, in terms of wind speeds, et cetera, et cetera. So we, in a way, were using this huge number crunching algorithm, machine learning algorithm, that have been used, for example, in medicine to see the patterns between the signs, maybe, and cancers or things like that. We can use similar powerful algorithm to learn what is going to happen. So you can plan your maintenance, preventive maintenance, lowering the costs, et cetera, et cetera. So it's not a crazy idea of mine. I'm just applied it to a different system. And actually, the algorithm that I've used, I've not gone into the details here, but have been used in the oil and gas industry to finely tune the water pumping into oil reservoirs, increasing by 20–30% the revenue has been tested on a real oil field. So I'm just taking that and applied it to another industry, and so far seems interesting.
Great, thank you. Maurizio, do you want to come and join
Sure.
us in the panel? Questions to the floor, any questions? Sir.
Trafim from Western Constructions. My question is to Mr. Ainsworth. As to the KPS system, how does it handle launching, landing, and no wind conditions?
Did you catch that?
Yeah, I did, yeah. Are these on?
Yes.
Right. Launching and landing, can I just say at the moment that's fairly proprietary, and there is there are several patents going through on that, so I'm not going to answer that at the moment. But low wind conditions, yeah, it depends on how long the low wind condition lasts for. The kite will actually generate enough lift even in very low conditions to keep itself aloft, and even with a small amount of parasitic power, it can keep itself aloft. But do you actually want to do that for 2 or 3 days, or would you just rather bring the kite in and dock it? So we actually have a range of options for the low wind conditions.
Thank you. There's the mic coming.
Hi there. For David Ainsworth again. Life of the kite, how long do you expect this to last? And I'm guessing you've got some system for loading new kite cassettes or something?
Yeah, so life of the kites at the moment, in our levelized cost of energy modelling, we're predicting 4 years. But the material results we're seeing at the moment, we would be fairly confident that will actually stretch and reduce the levelized cost of energy quite significantly. But also with the kite itself, the life is very much dependent on the, a suppose, the SN curve. Being really, really simplistic about it. So even with condition monitoring, they could actually last quite a lot longer. So in very, very windy conditions, they may be closer to the 4 years, but in low wind conditions, they could be significantly longer lived.
Other questions? I've got a question for Richard. So looking at what's out there in terms of technologies, because you had some pictures of different types of devices. Which ones do you like the look of and why?
We haven't looked at it enough to have a firm opinion on that. I think we need to be conventional in the foundations. I think avoiding yawing, I think having omnidirectional absorbers, I think having absorbers which are not exciting the modes of oscillation which are damaging for a wind turbine. The actual little bit of heave up and down point, not that big a deal. Pitching back and forward, gyroscopic, more of an issue. So I guess not seen anything that's completely convincing as yet.
Okay.
But can imagine some better ones. But I think the exciting thing for wave energy is that it allows you to think very differently about how to absorb, and the scale of these foundations gives us a natural phased array where you have absorption in a number of places, which has, in a very different way to multiple rotors on tidal or wind turbines, a potentially huge gain in the absorption from the whole system. So I think there's some very exciting developments possible, but early days. I mean, I think what we're trying to do, this is a thought piece at the moment, is there real appetite to look at this and shake the tree and see what we can find? And if there is, I think we could see some pretty spectacular impacts on deepwater wind cost of energy.
I thought the Californian data that you had, which had very seasonal difference, was quite an interesting.
Yeah, I mean,
quite an interesting one, because in the UK you don't tend to see that, do you?
No, I mean, we're very used to the UK, there being actually amongst, in the globe, it's probably the closest correlation between wind and wave resource, actually is the North Atlantic, the sort of eastern edge of the North Atlantic. Everywhere else in the world is actually, that correlation is a great deal weaker, and seasonal effects in particular are not as dominant. In California, what you're seeing there is that you have a lot more thermal winds, 'cause it's hot, and you have a lot of swell coming up from the storms in the southern Pacific during the summer. And the way that those two interact together actually work to your benefit. Australia and New Zealand are completely different again. It's about the low pressures circling the globe at higher or lower latitudes, but actually there's only maybe about a 2-to-1 summer to winter variation. So I think a bit more analysis of this could show up some surprising benefits above what we have in the UK.
Okay, thank you. Any other questions? Yes, sir.
Hi, my name's Graham Wilson. I'm from SSE. I've got another question for David. I think the concept's really, really interesting. I'm looking forward to hearing how the trial goes. What I'm interested in is scaling. So obviously for traditional turbines, weight's a big limiting factor. What do you think the factors are going to be for kites? And also, what do you think operation and maintenance is going to be like, especially when they're deployed offshore?
Yeah. Okay, so with respect to scale, we've done some work with our friends here. I mean, we think sort of pushing this to 6 is probably realistic, but it's challenging. Even at the 3 megawatt scale, we are talking about kites with wingspans not far off that the wingspan of a jumbo jet, so they are getting quite large. But we think they are manageable, and we can actually do that. The kites of this size have actually been used for kite traction systems. For ship traction systems. So we're not too scared of that, really. I think they've been demonstrated that sort of way. Second part of your question was
operation and maintenance.
Operation and maintenance. Yeah. So when we look at the offshore levelized cost of energy, what we've projected is that for every 30 systems we have installed, we have a spare one back at port. And we actually have a dedicated maintenance vessel. So we are projecting that basically on a year, in the early days, on a yearly basis, we go and unplug one system, bring it back to shore, and change it out for another one. And that's the maintenance philosophy that we're taking. It's probably not too dissimilar from Richard's philosophy at Palamis all those years ago. And there are some offshore floating wind developers who are actually looking at similar approaches where they actually unplug them and bring them back to shore, even at 7 or 8 megawatt scale. So we think that's fairly feasible. But as the technology matures, we see no reason why these things shouldn't be sort of 2 to 3 years between maintenance periods. We move more to a non-conditioned maintenance rather than actually a scheduled maintenance process.
And do you think there's a lot less can go wrong with this type of technology?
Sorry, I missed that.
Sorry, can you say?
Sorry, do you think there could be a lot fewer failures with this type of technology than with traditional turbines?
You ask me that question again in 12 months' time, because that's what the process is done at Westfair at the moment. So this year is about decommissioning. It's about commissioning the system, debugging it, and then basically going into a short period of where we actually throw all the upgrades we can at it over the winter period. And next year we're going to be starting a controlled phase of operation where basically we say maybe on the 1st of May we're going to run a 4,000 to 6,000 hour controlled process where we say that's what the operating period is, that's what the maintenance regime is, and actually come up with some really hard and fast mean times to repair, availability numbers and things like that next year.
Just to come in off the back of that, I mean, I think David might be understating the potential benefit to O&M cost of the strategy that they're adopting. This is something that we looked at a huge amount in Palamis and in wave energy in general. And actually, the established wisdom of you carry out the work on site is actually totally the wrong approach. And if you can recover the system to sheltered water, you spend a lot less time, a lot less money on boats, and you spend a lot less time waiting on weather. So if you can remove a system in, say, an hour, in 2-3 meters significant wave height, and reinstall it in a similar period, in a similar wave height, suddenly this just opens up a much, much lower cost, higher availability regime, and I've got a feeling that will benefit this system.
Yeah. Basically,
inconceivable with a fixed onshore turbine. I mean, patients get treated in hospitals, cars get fixed in garages. This is a big benefit that you should be pushing hard.
Thank you for that, Richard. Thank you.
I don't work yet.
The other thing to say is because you're replacing or planning to replace a kite every 4 years, you get a degree of innovation happening in something that historically on a conventional one you're stuck with a blade and a certain blade profile and what have you, and you don't have the ability to change it that easily. I know some people like Energy Contour want to stick an extender on your blade and some options like that, but I think...
Yeah, that's right. So early technology adapters won't be locked into that technology for 20 years.
Yeah.
So they'll actually see the constant evolution as we go through the life cycle of the project.
Good.
Yeah.
Thank you, David. Other questions? I've got a question for Tim. Scale, I would like to ask you a question about scale, because generally, I'm just concerned that a single turbine, so a single rotor is getting pretty big. If you're having to cope with 2 rotors, how does that impact?
Sure, understood. I think there's 2 things there. I think going for a multi-rotor doesn't necessarily mean that you're trying to go larger in terms of swept area. I think in the drivers in wind are very much that you might, rather than going larger, you would substitute a number of rotors for a single rotor, potentially with the same swept area. So it's not a mechanism to go larger; it's a mechanism to reduce costs at the same.
Yes, your driver is a cost of energy one. Yes. That's interesting. I think, the blade I talked about, the 88 meter one that's being tested at or catapult. Yes, you think 88 meters, and then you think, yes, actually, how big is 88 meters? They are absolutely enormous, and I think we've always thought there'd be a limit sometime, but we've never hit it. So we've continued to build bigger and bigger things. But thank you. Any other questions? 2 minutes. Got 2 minutes to go. Anything at all? Do any of the panelists have questions for the other panelists? Well, I'd like to thank you all very much for attending. I'd like to thank the speakers for speaking, and if we can thank them in the usual way. But before I do that, I just need to remind you that the next session that's on in this room is start at 3 o'clock. That's Offshore Wind 6. And the presentations will be made available to you as delegates, but the presenters need to give their permission for that. So they will be asked to do that by the organisers. But I'd like to thank you all very much for your contributions.